And there's the heap, and this is the
Sorry,
sure.
Renee. I should have asked. Somebody asked if I could, and I hit the button, and it's recording process. I should be way better at reading. I apologize. I wouldn't start over, but as long as you're okay with it, I'll leave it record. If not, I can stop. Totally up to you.
I'm totally fine.
Okay. Thank you, Renee.
Good.
Sorry for forgetting that part, and thank you for reminding me,
No.
Manny. Sorry.
So the heap, just to continue here, the heap is the part what you think is Java main memory, right? This is basically where everything is stored and everything is done, which is actually not true. But it's basically what the Java programmer has as a notion of memory. On the right side, you see a computer, a classical, laptop, for instance. It has multiple cores. Each core maybe share a die, so they are packaged together. Each core has registers. That's the fastest memory you can get. Doesn't get any faster than that. Registers are basically very limited memory, so really just a couple of bytes you can store there. And you have 3 levels of caches. And typically, the higher the level, the slower it is, but the bigger. And level 3 is typically shared between cores. This all then basically goes against memory. And most of the time, the CPU doesn't see real memory, it sees virtual memory. So the operating system is managing the memory in a way that if you ask for memory, you don't get real memory, you get virtual memory, and that's it, period. You don't know where you're writing to. It's just basically could be anywhere. It's just basically guaranteed that you get memory. That's it, period. So now you have to basically transition the left model to the right one. And this is what the Java language specification does in chapter 17. And this is where the compiler builders struggle with, because they have to map the limited world to the very fancy and fast one. And later on, we will see a couple of more details about machines and memory and why this is so difficult. And of course, you have the right screen. Here we go. So where do we live? A couple of things first. So this is a typical Java class. It has fields, and these fields are always on the heap because your entire object is on the heap. If you talk about Project Valhalla, which most people might not have heard of, it's basically something to improve the performance of Java. Project Valhalla will basically give us classes that behave like primitives at the end of the day. Things will change, but so far, so good. We basically have fields on the heap. If you call a method, you have the parameters on the stack. And for instance, if you pass on any kind of object, it's only the reference to this object that's basically on the stack. The object itself might live anywhere. You don't know where. If you basically declare a local variable, it might be in a register, it might be in the cache, it might be on the stack, but it's definitely not on the heap. That's guaranteed. If you pass on your reference to a local variable, of course, the reference here now lives on the stack, but the real object is still anywhere. You don't know where. If you create your own array, for instance, the reference to the array is definitely on your local stack. It might be also just kept in a register. You don't know if this is basically moved to the stack. And the stack basically, just to explain, this is an exclusively reserved memory area just for your thread. Nobody else can ever see it. It's just basically exclusive memory. So if you say new array, the thing is, this array can be on the heap or it can be on the stack. You don't know. Java makes the call here depending on what you do and how much memory you're allocating. If this object will never escape the method and it's not big, it might live on the local heap, on the local stack, which basically avoids garbage collection and makes things really, really fast. If this is a larger array, it will be definitely placed on the heap and it becomes slower. And of course, the last one, which is just a normal object, and the instance here will be definitely on the heap. Doesn't matter if it escapes or not. The reference itself here, stack, or register, but this guy here is definitely on the heap. And anything that's on the heap can be shared. There's basically a risk that, 2 threads can see it. So we keep this in mind. Good. So And by the way, typically often there's text next to what I present. This is just a summary of what I just told you, just in case you want to look this up later. And sometimes things are a little bit asynchronous when I present this. Good. So atomicity. The big question is, what kind of operations can you divide in smaller ones, and which are basically just one operation seen from the computer point of view? So first question, if I have a variable on the heap, so it's shared, of type long, and the first thread writes 2 to it, and the second thread writes -1 to it, what would be the outcome? The possible outcomes. Will this be always 2 or -1, or is there any kind of in-between state?
It'd always be one or the other, right?
No, it's not.
No.
Because a long, normally, depending on, of course, your virtual machine, is 2 bytes, is 2 times 4 bytes. It's basically 2 ins together. You write, of course, the high part first, and then you write the low part, and the other thread might write this way. And at the end of the day, the main memory is screwed up. This is a 32-bit problem. So if you're running on a 64-bit VM, that's not longer a problem. But because you're Java, you don't know where you're running. You can't make the assumption that this is a proper 64-bit long. It could be basically a 32-bit long, which is basically just 2 integers together. So this is important to know. It's not an atomic operation if you write a long. Good. By the way, possible outcomes are here. So, good. So is this atomic? It's an integer, and we know that an integer is basically just 4 bytes written to the memory at once. So is this atomic? Is it guaranteed that this is an okay operation if 2 guys are doing this at the same time?
I'm going to say no, because you're doing a read and a write. Yeah,
right. So at the end of the day, what the compiler does, and this is not the Java C compiler, that's really the Java Virtual Machine C1 or C2 JIT compiler. It puts this basically in a local state, and this is the bytecode first. So basically we get the field, put it on the stack, we put 1 on the stack, we add the last 2 elements of the stack together, and then we put the stack back to main memory. If you see this as assembler code, it looks like that. So we basically move something from a memory address to a local register. In this case, it's EDI. And then we increase EDI by 1, and then we move basically stuff back to memory. So if basically 2 threads are doing this at the same time, you never know what will be the outcome at the end of the day. The only thing that's guaranteed that this move is an atomic operation. There's only 1 state that can arrive. But if 2 guys are doing this at the same time, you don't know which will win. So good. So if I just do this on a local variable right now, is this atomic? One, two, three. That's basically the bytecode for it. So it's way smaller. And this is the machine code for it. So we basically have to move 2 into a register, and then we can add this register to another register. So what you already know is that our long local is local because it's a register. It's not a memory address at all. It's just basically really, really close to the CPU. It's basically the cheapest memory you can get, the fastest one. There's no memory address ever used to store your local long. And this is all called read, modify, write operations. And what you have to keep in mind is everything the CPU does is only what the CPU can do. Memory is an idiot. Memory can't do anything. Memory can only deliver or receive. Memory can't calculate. This will change in the future. So we're currently working on memory that basically is able to calculate things for us because it might be more efficient than moving stuff to the CPU, doing calculations and moving it back. This will be probably very useful for artificial intelligence applications, but at the end of the day, basic CPUs read, modify, write. you can't avoid this, at least not at the moment. This also means one Java command doesn't mean it's one CPU command. And then now the interesting question, if I do a new operation, which looks like this. So I have a point class that's shared, and I do a new point. Is this an atomic operation? Is this basically compact so that nothing undefined can happen?
My vote's yes.
So this is the code that will run at the end of the day. So we create a local variable, could be a register. We will basically allocate memory, and then we initialize our object. And then we basically write shared. So it's definitely more than one command. It looks kind of atomic safe, right? Because, you know, as soon as you write shared, local is very defined. So nothing bad should happen. And it's not atomic, and we will get to the spec later. And it's very broken, and most of the code you might have written so far in your life will have suffered from this problem. Maybe not directly, but definitely indirectly. Good. Visibility. What do other threads see? The spec tells us, and this is actually really from the spec, no out of thin air reads. So each read of a variable must see a value written by a write to that variable before. So in this case, Java says, I will never present you any garbage. So if you compare this with C and you allocate memory, the memory might be garbage. So it could be anything in there. Java will guarantee that if you ask for memory, it has a clean state. And this is a very defined state that's defined in the spec. So if you allocate, let's say, an integer array, it will be 0 all across the board. If you allocate a primitive, it will be 0. For instance, a Boolean will be always false. An array will be always initialized with the values of its members. And even every reference at the end of the day is initialized before. It's either null, so there's no garbage, even so you have not written to this reference yet. So it will never be garbage. So it will be either null or something defined. The thing is that really differs from other languages. Of course, Rust is taking care of that. This is the reason why Rust is so popular, because you can't do garbage anymore. Java here is also very safe, but EOS at the end of the day is the operating system is not doing the same thing for us. So Java is basically providing this on top of the operating system. So if you write, or basically you ask the OS with a very low level language for memory, you get basically garbage. And at the end of the day, you might not even get memory if you ask with C code against the operating system, say, hey, give me 4 kilobytes. And it says, okay, here are 4 kilobytes. They might not even exist yet. So in Java, it's guaranteed that this actually exists. It's absolutely clean memory. The problem here is if you really want to do very optimized programming, it's almost impossible to do, because if you allocate 4K, they have to be cleaned first. And this basically takes quite some time. It basically works against the CPU caches. And so it's very bad at the end of the day. Of course, you can do reuse. So basically reuse your arrays or some kind of other objects you might have. But then, of course, they are not immutable anymore, and you run into totally different problems. So that's very important. There's always clean stuff going on in Java. By the way, this is also one reason why when you declare your fields in your class and you write int local equals 0, doesn't make any sense, because it's already 0 by definition. There can't be anything else in it. Only when you want to have a Boolean that's true, you can actually, or you have to set this to true. Everything else will be pre-initialized. And Java in this case runs the code even twice. So it initializes your local variable with 0, and then you basically declare, I want to have 0 in it, and executes the code again. It makes things even slower at the end of the day. Good. So immutability. Can you close an object in a way that you cannot write to it? And it's very guaranteed at the end of the day that this has a very defined state. This here is probably similar to the constructor problem we initially discussed. But the problem is that the left side is not an immutable object. The thing is, at the end of the day, this is an immutable object. You might now ask, what the heck? Because on the left side, you can never have an x and a y with a different state than what you presented in your constructor. Right?
Is this because of reflection?
Nope. Well, yeah, reflection is a totally different story. We just talk about clean programming at the moment. Reflection is a different story. Obviously, you can really work against the VM and do nasty stuff like reflection. And you can even open final, by the way, with reflection, which of course is bad, but you could do it. No, it's not about reflection. And we will learn in a minute why this is a problem. By the way, this would be a very condensed version of the code, which is still totally fine and totally great. By the way, Java will optimize or de-optimize your code in the sense of it will get rid of get X and get Y anyway. So it will never call your methods at the end of the day because it sees doesn't make any sense and will directly read the variables at the end of the day. So this is just candy at the moment. Good. So what is this final? Final guarantees basically one outcome and one outcome only. So if you do this on the left side, and you say final guarantees, there's only one possible value ever written to this variable, because final means you can't change it afterwards. So write once, always read, never write again. So the problem is, as you have learned before, we initialize memory first. So Java is writing to X and Y first with a 0. So worst case, you would see this 0 because your assignment is a little slower than the initialization of Java. So there's basically a time where X and Y are 0, and then you write basically as part of your constructor. And now you might think, hey, if I just see this code, it can never happen. It can happen. And this is one of the tricks where we need fences at the end of the day. And I will explain fences later. We just have to introduce this concept. So this is really immutable. If you put final next to it, if there's no final, it's probably immutable, but it's not guaranteed to be immutable. Okay. Now the question is, when are things visible, or when will be things visible? So for instance, if I write to a shared variable 20 and then 40 and say print shared, what does Java do? Right. In this case, Java basically says, let me build a dependency graph, because when I compile the code, you might have put stuff in which doesn't make any sense. So it knows that line 4 depends on 2, but nobody cares about line 1 because there's no dependency. So Java decides to drop line number 1 because it's single thread consistency. As we learned before, is if you don't tell me anything about the code, it means it might be multi-threaded. I deal with it as it would be single-threaded, and the outcome of this is always I print 40. Doesn't matter what you do before that, because there can't be any other outcome. So I can safely drop 20, and the code is still the same. So Java will remove basically line number 1 and compile the code and just run it. So there is never a 20 written to the shared variable, because you don't say to Java, I want to have this written. So Java optimizes your code and just drops it. By the way, this is even fancier, and this is absolutely legal. Java can basically decide, hey, why not print 40 first and then assign 40 to the shared variable? This is absolutely legal code. It's absolutely the same outcome, and it can be done because you haven't stated that you are not want to have this optimization. So Java will do whatever it takes to make your code faster. Cool. So this basically leads to the following problem. If you have this nice array and you sum up the content of the array in a shared variable, that this might not work the way you expect, because Java will do this. It will create a local variable, probably a register, will sum up everything in this register, and then later on write this back. So the left code is definitely not what runs. Never ever, because it's just horrible slow. On the right side is way faster. So Java says single thread consistency. You haven't told me anything about multi-threading. Let me just do my work, and this basically means I do it this way. Because at the end of the day, writing to memory is insanely slow, so Java avoids writing to the memory. Good. Interesting question. Can this be 30? Is there a way that basically the square of any kind of integer or long can ever be 30? Not talking about overruns here, of course. Yes, it can be. Because this is what a compiler does. At the end of the day, we have two local variables, and then we multiply them, and then we write to x. And x is basically local storage, so we don't care. And if you now have thread 1 and thread 2, and they run basically their code in that order, the square of 5 can be actually 30 at the end of the day. So this will happen. And now, by accident, this is single thread consistency, so Java is totally fine. So by accident, in reality, Java does this. We shared once and then use the local basically to calculate the square. And we can prove this by just looking at the code Java generated, move the memory location into a register, and then multiply the register with itself. And boom, everything is cool. And by the way, as you can see here, we are not going to move the data we just basically calculated out of this register, because, you know, the register is local memory, and we just basically said X is local. So there's no reason to write this to any kind of main memory. We just keep it there because we later on might need this. And if it's in a register, that's the fastest way to do things. Okay. And we will see this code again because, you know, for a reason. So the most important optimization Java does is basically try to simplify things as much as possible. So we have our famous array, and Java C does the first thing. It basically says, okay, let's turn this into a classical for loop. And then basically Hotspot sees this and says, okay, I don't want to access the array too often. So let me store this array reference locally. And of course, the length can never change because it's an array, it's static. So let me store this locally as well, and then run the code. So it's definitely not the code you initially programmed. It's an optimized version of it. But single thread consistency, you get the result you asked for, and it's always the same. Good. So this is basically what we think Java does. And in most cases, it will actually do this. But if it really gets fancy, it will actually do this. So it will unroll your loop and basically say, hey, a loop, I have to jump back all the time. I have to make comparisons all the time. Let me just get some of these out because it's just expensive. You know, jumping in code is really expensive. So Java will basically unroll this into two loops. One loop might have a length of 4, and the other one is basically then to finish up what might have been left. So you can see it's Java and the
question there. Yeah, I haven't looked at the hotspot compiler for a while, and this makes sense to me because, well, it was quite interesting. If they definitely look at the processor in the past when I looked at the code that they were after, so as to understand whether they use the processor stacks or heaps or etc. Is that, do they still do that?
Yeah, they still do that, and we will see a couple of examples a little later. So, and this was basically the presentation I've given before. So the first one, it's really when Java starts, it evaluates what kind of CPU it sees. And then it decides what kind of assembler code it might bring to the table at the end of the day. So if you have an older CPU, the code might be compiled differently. If you have a newer one, it might be this or that operation. So Java, for instance, makes the call. It has one of these fancy vector instructions available, or if it has, you know, crypto instructions available on the CPU. If it finds that, it will use it. If not, it will fall back to some assembler code it brings to the table. Does it answer your question?
Yes, it does.
Good. So, and here is the really the bad example. We have a loop, and this loop basically is on a shared variable, which is called done. And we loop until this is basically true, or yeah, in this case, true. The problem is this is what Java does. It reads the variable, stores it locally, and then the while basically is an infinite loop. Because you have not told Java that this is actually something it shouldn't do. So it tries to optimize the code. And optimization means never read memory too often. Therefore, keep a local reference. Everything is cool. And this is then broken. Good. So the Java language specification states, to some programmers, this behavior might seem broken, obviously. However, it should be noted that this code is improperly synchronized. So everything you have seen is basically bad Java code. And the problem here is that we can actually write bad Java code because Java has been inspired by C. It is 25 years ago. And modern languages like Go and Rust know that this was kind of a bad decision. So they now avoid this at all costs. And they give you basically compiler constructs and verifications that this cannot happen anymore. But Java actually still has the, capabilities of messing with your code, or you mess with Java's code. The problem is that at the end of the day, the modern compiler and microprocessor performs optimization that can interact with your synchronized and or unsynchronized code in a very incorrectly way. And so you get this very paradox behavior at the end of the day. Good. Cool. So, and this is basically for me, shared access, not concurrency. So you might think, okay, let's multi-threading. Of course, if one thread accesses a variable, the other one should not access this. So I put a synchronized around it, and that's it. And that's not what shared access or concurrency really means. At the end of the day, it's about visibility. So there's basically a variable, it has a state, and there's another thread that wants to see the state. And this other thread might live on another core and might see other caches. So it might definitely not see what the other thread has written initially, because there's a cache in between. And if you don't do anything about it, it just reads its old cache content. It is happy. So it can't see the changes the thread A has applied to a certain state, because you haven't declared the state as being a shared one. Only by accident you're sharing this variable, but you haven't declared it shared. So in Java, it's very important that if you want to share, declare. Oh, this rhymes. Good. So, and this is where this so-called happen before magic happens. So there is something, we will later see this. Java establishes a so-called happen before relation. It will basically take care of the code and make sure that when things happen, everyone can see it. Good. So, and this is basically the next level of optimization now. So for instance, for this code with two shared variables, what does Java do at the end of the day? It basically says, okay, let me plot this and let me see what happens. So print x depends on a true state, and the true state depends on shared x being larger than 0. And this depends on shared x being 2. Ooh, why? This is great. And shared y? Nobody cares about shared y at this moment. Okay, then let me do certain things to optimize the code. And all these examples are absolutely legal code, because you haven't told Java that what you accidentally shared is supposed to be shared. So Java can actually say, hey, shared y can be done after the if statement. It can totally drop the if statement because the result is always clear. It can even say print 2 and then later on write to x. It can also just open the if statement and append an else for a second branch to set y as well. And then, of course, it can also reorder x and y because it doesn't change the outcome. So this is all totally legal, and your Java compiler might actually do this. And sometimes it might just compile one version, and later on it compiles another one because it actually sees, hey, this is way cooler and it's way faster. So it will actually do all of that. Good. Quick detour, modern machines. So we have basically a CPU, we have caches, we have memory, we have hard drives. And it takes about 0.4 nanoseconds to get to actually run a CPU cycle on a 3 gigahertz machine. And then it takes about 0.9 nanoseconds to get to a cache. Of course, nanoseconds is really hard to get a grip on. So let's humanize this. And here you can see if a CPU cycle would be 1 second, Going for a cache would be 2 seconds. If we go for an L2 cache, it's 7 seconds already. If we have to go to L3 cache, it's already a minute. So if I read basically something that's not in the cache, it takes about a minute. And if I have to go to main memory, I might spend 4 minutes waiting. And if you just basically calculate the number of cycles, it would be 4 times 60, 240 cycles I'm currently waiting. So the CPU is not really fully utilized. And if you have to go to hard disk, it's even worse. So the thing is, at the end of the day, Java and every kind of compiler you have, doesn't matter if it's C, C#, Rust, Go, they all basically try to avoid memory access because memory access is evil in the sense of it's way too slow. So they will do basically everything necessary to avoid this. And this basically means if you have any kind of state, they try to move the state as close as possible to the CPU. And if you don't say that this state has to be seen by someone else, it will remain as close as possible to the CPU without being moved to your computer. Just save time as much as possible. And the second thing is, this is a modern computer. It's not really a modern computer anymore, but you know, the modern computers work similarly. So you have execution pipelines. So a modern CPU doesn't do one thing at a time. It can do multiple things at the same time. So for instance, it can, well, let me just basically show this fully to you. What it can do is, if it basically sees your first command is a multiplication and the second command is an addition, and there's no dependency between them because they use different data, I can run this at the same time on my CPU. So we have multiple execution units. They can be fully utilized. So I can basically do concurrent operations on your code that was never intended to be concurrent, that runs within one thread. The CPU will basically break this up and turn this into a parallel program at the end of the day. And because certain executions take a little longer or a little shorter, you might get a certain out of order execution. So it basically means if you have an instruction that does an addition first and then a multiplication, there's no dependencies between these two. It might be that the addition finishes first or might be placed first, even so in your code, it might be second. And this is the reason why our new initially was broken. Mark, are you still with us? Yeah, you are. Good. So here's our new example. This is basically our pseudocode, and this is the way it runs. And now this is what the CPU does. Because we allocate memory and then later on we write memory, the CPU knows writing memory is expensive. So let's start this as soon as possible so we can finish in time. This basically means the initialization of the object with all the state can be done later or can be done after moving stuff to memory, because this can happen in parallel. So we will basically write to shared with the local reference. And in the meantime, while this is basically transferred through the computer to main memory, we finish initialization of our object. This basically means there is a moment where you can see the state of your final variable being 0, which is the non-final variable being 0, because the computer reorders things. And now the magic happens. By the way, this is also why this famous get instance is totally broken. If you have basically a variable that's an instance and you do this, like, if this is null, then synchronize, write it, and then return it, this is totally broken code, because this is what the computer does at the end of the day. It writes to the instance and the initialization is not done yet. That basically means you leak an uninitialized object to the rest of your program code. And therefore, this code is absolutely broken. Most people will say, hey, this runs fine. Yeah, of course it runs fine most of the time, but it's not guaranteed to be flawless. There's a difference between bug-free and proven code. It's just... Okay, so this is the reason why we need fences. And fences is basically a way to tell the computer, hey, I don't want to have this reordering thing you are doing most of the time. So give me guarantees. And so on the left side, basically, we have a producer that does shared data, and then the shared data done is true. On the right side, we have the consumer that basically waits for shared done and then prints out the stuff. On the right side, we then suddenly see, hey, the producer decides to reorder the execution because it's totally legal. And then, of course, the consumer basically falls flat on its face because suddenly shared done is done. And then we print out garbage because it hasn't been written yet. Good. So we have to prevent this reordering, and there is our tool set. It's called a fence. And of course, nobody has heard of fences before. There is no Java keyword that's called fence. I just basically give you a virtual description first. So we basically put in a fence between shared data and shared done. So the computer knows, hey, I can't reorder. I have to keep this order. And then basically on the right side, I have to make sure that when I read shared done, I actually read this again from main memory to make sure I read the latest state and not reading my local copy. And this is the same for shared data, because shared data is basically something that I have to read from real memory to make sure that I get the latest state. And these fences, there are basically 4 types of fences. And you know, Intel has different fences than ARM. And this is also the reason why compiling just from Intel on ARM and getting out a working VM is impossible. You have to rewrite some of the VM code to actually make this executable on ARM, because it has different fences. So it has to have different assembler code at the end of the day to basically make the result consistent. So it's not just simple, basically recompile with a different instruction set and maybe just hack a couple of updated assembler code. No, you have to rethink a couple of things within the VM. So if this is an ARM CPU, the code has to be done differently or be recompiled differently, so you get to the same consistent result. Same for RISC-V and stuff like that. So it's not a trivial port at the end of the day. Good. So and this is where we get to the fences. And the fences have name in Java, and there is a volatile, that's a fence. There's a synchronized, that's a fence. We have a final, which is a fence. We have atomics, and we have var handles. And the last one, I'm just dropping, they're brand new, and you can fill an entire presentation with var handles. So we're just dealing about the first 4, because they're the most important ones. Each of these does different things, so they're not the same. So you cannot just basically say, okay, let me use a final instead of a volatile. That's a totally different story. Or an atomic, switching out this for a volatile doesn't work. Therefore, you have to know what these do at the end of the day. So a final is basically, by definition, you only see one state. You will never see the initialized state. You only see the final state, period. A volatile basically ensures that when we read data, we read it from main memory. If we write data, we always write this back to main memory. There's no in-between caching going on. Or to be precise, there is caching going on, but the CPU is basically managing the cache consistency. So if someone else updates main memory, the cache is dropped because it is marked as shared data. So the CPU will then take care of optimization on its own discretion. If you do synchronized, it's similar to volatile. It basically says, okay, if I see a synchronized, I have to read everything from main memory and I have to write everything to main memory. But in addition, it also prevents multiple threads from entering the same code area. So volatile doesn't do this. Final doesn't do it, but synchronized does. So synchronized basically prevents threads from running the same code at the same time. And we have atomics. And atomics are once again kind of volatile objects, but in addition, they completely encapsulate a read, modify, write operation. So as we have seen at the beginning, we have basically 3 statements that are necessary to increment something. An atomic version is basically one statement at the end of the day executed on the CPU. It's a very special statement. And the CPU takes care with a special operation in hardware to carry out this as a very atomic operation. It might not be a really atomic operation, and we will see this example later, but for you as a programmer, it's basically suddenly an atomic operation. It's no longer read, modify, write. It's basically just an update. And then the var handles, which is all of this before in code, so you can do really nasty things. Hence, var handles is something for a different presentation. Cool, good. So let's deal, and we still have plenty of time. So let's deal with final and freeze first. So on the left side, that's the code we discussed before. On the right side, now we have final, and the final puts in a freeze operation after the object initialization. That basically means the compiler can no longer move the share up to optimize the storage operation. And it also means that the CPU itself cannot move this either. So Java doesn't move it, the CPU doesn't move it, because there's an operation that basically indicates hands off, the order has to be, this has to be the order of things, basically. Okay. What you can still do wrong is in the constructor, you can basically still leak your object to another place by adding it to the cache, for instance, which basically leaks the reference, but the initialization of the object is still in progress, which the final doesn't prevent. So it's always important that you're not doing such things like leaking the reference of this object to any kind of other object, because it would break code once again. Even so, it runs fine most of the time. Good. Volatile. And this, by the way, is the keyword that has been redefined from Java 1.4 to 1.5. So this is basically one of the keywords that has been in the language, but got a different meaning. So the volatile keyword is used to mark a Java variable as being stored in main memory. That basically means read it from memory, write it to memory, nothing in between, and let the CPU deal with all the optimizations in the sense of, if you can cache it, cache it. If the cache is basically, invalid, take care of that. And this will basically fix our famous instance problem, the double-checked locking, because you now declare instance to be volatile. So you always read this from memory. This basically makes sure that you cannot leak it, because defense prevents reordering. Hence, you have to finish the object before you actually assign it to an instance variable. Therefore, it's safe to be used this way, even so it might not be the the fastest version of code. There's a holder pattern or something like that you can use instead, which makes your code way faster. But sometimes it's kind of impossible to apply this. So you have to, for instance, initialize a singleton class with a certain state, and the state really depends on the moment, and therefore you have to sometimes do this.
Hey, Renee.
So the full behavior of volatile.
Sean, oh, sorry.
Yeah.
Go ahead. Sean has a question.
So I have a quick question. Since your volatile forces a read and write to main memory, because cache could be out of sync between cores, does that sort of, well, I'm guessing performance is decreased.
Oh yeah, because as we have seen before, it's 200 cycles you need to read from main memory and write to main memory.
Right.
It basically means you have probably 100 to 200 cycle penalty on that.
So with these fences, do we want to reorganize our code to avoid circumstances that require fences?
Yeah. Well, the thing is, at the end of the day, every fence costs money, right? If they would be free, then of course the language would just bring them to the table and say, "Hey, use this is built in," So it costs, and because every fence has a different, impact. Like synchronized avoids concurrency, volatile basically writes to memory, synchronized too. Final just only closes the constructor, does nothing else. So we cannot use final for anything else. And an atomic is basically, and we get to this, it's basically an optimized read operation, read modify write operation. You have to be careful what you do and when and for what reason. If you write, and you want to actually do this, functional programming talks about immutability all the time. Basically, right. As long as you have only immutable objects, you are not going to have any problem synchronizing. That's because right. This is absolutely safe, unless you drop the final statement. That's a different story. But you don't need a volatile, you don't need a synchronized for proper functional programming. Obviously, it's really hard to program that way. Hence, you still need the statements sometimes.
I see. Thank you.
Renee's use case here, if you need a singleton or something that acts like that, then yeah, that's the best way to, that's trade-off, as he says. Actually, another place, if you want to see lots of that looks and understand the use cases, go look. There's some various things in Spring, for instance, you know, they like configurations, things like that, you know, hey, you don't want to read the database or the property files, your configuration all the time, but you've got to load them in at some point, and you've got to do some kind of synchronization to make sure that there's not any premature reading of, you know, of these objects, so that your code gets off on the wrong foot, or parts of your code do.
And Sean, what basically happens here is probably the CPU or the CPU caches will see that you have written instance, and then everyone has this suddenly in its cache, and nobody ever writes to instance again. So the cache synchronization that happens naturally on the CPU, so you have stale memory, you have to get rid of it, you have to reread, says basically, yeah, no, this cache line is still safe, use it. So you don't have to go to main memory, because your cache basically is optimized for that. Java will never put this into a register, so it will always basically issue a memory move operation, but it could be in the cache, and the cache could be extremely hot because it's L1 cache that holds this information. So we have a very small penalty, maybe a 4-cycle penalty, not necessarily a 200-cycle penalty, because the cache synchronization of modern CPUs takes care of, you know, invalidating things if necessary without the compiler or you interfering with it.
Okay. So let's say, for example, you have L1 cache associated with core 1 and L1 cache associated with core 2. Are you saying then will volatile invalidate a particular, like, how will that work then with the caching?
So basically the CPU has a notion where this cache is coming from. So it basically knows what main memory is basically associated with this cache line. So if someone writes to this cache line, there's basically a flag that says, you know, this is bad. And then there's a cache synchronization protocol running across the cores, and you can read this in AMD and Intel specifications. It's extremely complicated. And they keep track of changes, and basically as soon as someone writes, they basically invalidate the cache line, and then basically you have to go to memory to fetch this again. Then it will be placed in the cache again, and if nobody then writes again, it's safe to stay there. Okay. So it's not that the write immediately invalidates, it's just basically that the cache line will be marked and not used. And as soon as nobody writes again, the cache is absolutely safe. So there's hardware that takes care of cache synchronization. Same for L2 and L3. Good. So here's the full behavior, and you know, it's a lot of text. At the end of the day, when you have a volatile, what happens is everything that has happened before a volatile operation is basically refetched or made sure that this all is written to memory. So there's a happen before relation. So everything that happened before your volatile read or write basically also gets synchronized. So there is no half synchronized state of the data. Everything that was before touched will be flushed and will be read again. That makes sure that there are no dependencies between these objects that might be broken. So here in this case, we basically have 3 ints, and the last one is basically volatile. And because we know that volatile also tells the CPU not to reorder things, and the compiler, we see our first code here that basically says, okay, move our registers here to main memory, 1, 2, 3. And then have a lock, and the lock basically it tells the CPU that, you know, there's no reordering permitted, you can't do any fancy stuff here. That's basically very important information. Move this all to main memory, and if there's anything to invalidate. If you move days basically to be the first element here, so you basically, instead of saying this year, this month, this day, you say this day, this month, this year, you see that the code changes, and suddenly the lock basically moves up. So the CPU is free to do any kind of tricks below this lock line. So months and year can be reordered or optimized in any kind of other way. But still days is flushed to memory as a guarantee. So just by reordering the code, you can also define how much code is, or how much memory is reread in case of changes. But this is, you know, this is really cutting edge optimization, you probably as a normal Java developer should never think about that. Just forget that I mentioned it. If you're really cutting edge and you have to save a couple of bytes and transferring stuff to the memory, that might be some of the things you can do. But under normal circumstances, that's not your problem. Okay, so volatile at work, that's what we just discussed before. The problem is volatile cannot be used as a read, modify, write fence because we still read from main memory to a register, then we increment register, and then we move stuff back. Here in between, obviously, someone else can also have written to main memory already. That basically means that our increment is void, but we still write it back anyway. So this is not a correct counter. If you want to make this correct, you have to use atomics, and we will see this in a second. Okay. By the way, this here on the right side, as you can see here, initially our square operation is basically move from main memory to a register, increment or multiply the register with itself. So this is a square operation. If you're now volatile the shared, you get two move operations into two different registers, and then these both will be multiplied. So by declaring volatile, Java basically drops this optimization to read it only once because it's the same data anyway. It knows that this might be different, so read it again. And this is what volatile does. It always basically says, read it again, don't optimize this code. If this then comes from the cache, you can't influence this. This is a CPU task, but definitely it won't be optimized in the sense of I have to read it only once, and then I can multiply. Good. The famous synchronized. If you need a bigger region of synchronization, you have to probably use a synchronized block. And first things first, a synchronized block is insanely expensive. If you look at the assembler code that is produced for such a entrance and exit from a synchronized block, that's probably 50, 60 to 100 operations. So it's really, really expensive to go into a synchronized block. Not to talk about I have to read from main memory. So on the right side, we have an increment on a shared variable that's basically protected by a synchronized block. Or I can also write this differently, and basically instead of synchronizing the method, I can basically write this as a separate synchronized block on the instance itself, which by the way is the same, exactly the same code at the end of the day if you write this way. The thing is, two threads are basically unable to run the same code at the same time. So you enter the code and someone else is basically prevented from entering. Nobody defines what preventing from entering means. Java, and definitely also not the operating system, is not stopping the thread. What might happen is, for instance, that I am the second thread. I see there is someone in this block, and I might just open a loop and spin until the guy is gone. Because it might be way cheaper for me to spin a couple of cycles instead of sleeping and waking up milliseconds later to see that someone else left the block. So it's undefined what actually happens with this thread. It's not stopped. It has to basically pause itself, return control to the operating system, and the operating system might wake up it later, or it might be woken up anyway because there's scheduling going on, and then it might check its flag again and say, oh yeah, you know, I can enter the code, it's cool. Or, oh darn, I'm too late, someone else was faster. It could happen in theory that when you have a lot of threads running against the same code, that one starves to death and will never be able to enter this code. The chances that this happens are extremely low, but in theory, it can happen. But I guess nobody has seen this in practice. Good. One of the important things, you can only synchronize against objects. You can't synchronize against a primitive. The reason is an object has additional memory footprint, and this memory footprint holds state. There are basically a couple of flags that indicate, oh, someone is here in this code area, don't do anything. And this is basically how synchronization works again. It's just flagging an object as being busy, and nobody else is then basically working against it. That's the entire trick. So it's just setting a flag in memory. Someone else is running this code, and you just basically have to wait until this flag has been cleared. Good. And here's the key to the kingdom. The happen before relation. And I was kind of unsure when to explain this how, so I basically decided to do this now. So the standard basically says there's a happen before relation on memory operations such as reads and writes of shared variables. You can have synchronized and volatile as well as final, as we know. And there's also thread starts, thread join, which also calls the same operations, and they cause a happen before relation. So code cannot be reshuffled anymore. They will keep, the order will be kept the same. Everything that's above this fence stays above the fence. Everything below stays below, which is not entirely true, but mostly. And this is basically how a happen before relation works. And if you basically review code, just think in a happen before relation, you see basically volatile is synchronized, okay, this code stays there, this code stays there. Can this be consistent? Can this be consistent? Because concurrent code can often only be reviewed, it cannot be tested. If you see a genuine test that basically tests concurrency, it's often not really true or valid, because edge cases can never be evaluated safely. So it's always a review you need. So if you do this all yourself, most of the time you get things wrong. Hence, there are certain util concurrent classes you might want to use for certain things. And the rest is for later. We get to our synchronization again. And this is what you might have done before. You have a producer that produces data, and you might have a consumer that basically consumes this data. And now we have a problem, because synchronized introduces happen before relation. That basically means everything happens before the synchronized, happens before, everything after happens after. But it also says nothing about what happens within the synchronized. And this is now normal code again. You can reshuffle the code within the synchronized block as to your liking. If the compiler says, I don't like this order, it can reorder as long as the outcome within the block is the same. And the same is what the CPU does. So if you write basically this code, the problem might be that shared done has been set true, even so it might not be true. So you can be woken up before done is actually written, because lock notify can be moved and shared done can be moved. So the order of things can change. Hence, you always have to say, okay, shared done, what's the state? Cool, this within the synchronized block, so it's safe in memory. Okay, if this is not really set, sleep again, and then wake up again, sleep again, wake up again. And notify doesn't guarantee that the things before the notify operations have been really done. So you can actually also put lock notify at the start of your method, or in this case of your block. It would exactly do the same thing, no changes at all. So if you basically review code and say, hey, yeah, notify has to be at the end, that's not true, doesn't make a difference. Because then you haven't understood what actually happens within the virtual machine. Of course, it might be nice to review and might make sense, but at the end of the day, that's not the code that runs. And by the way, lock notify does not mean the thread is woken up. There's an attempt to wake up a thread. And there might be situations where the thread just wakes up on its own, and lock notify has never been called. This is also one of the reasons why you need this while share done loop, because you can just basically be woken up for no reason, and you don't know why, and then you have to check the state. So that's very important. And I suffered from this myself, so that's the reason why I know this. Good. There's also one thing that's called lock causaling. Because it's really expensive to go into a synchronized and come out of a synchronized, Java basically sees this and says, okay, we have a synchronized against the buffer, and there's another synchronized against the buffer. Let's do this. It's absolutely legal, because at the end of the day, there's no difference in operations. Same outcome. Because now we basically save us from entering this twice. And so Java now can once again reorder code. So your foo bar can basically be moved up at any position and still gives you the same result. The only thing that will not happen is that buffer will be moved around, because that's not legal. Good. And of course, Java can do even more. If it basically sees this code and it knows leaving a synchronized block is a darn expensive operation, I have to do a lot of things on the CPU. Why not doing some memory operations before that? So memory operations might be finished when I'm finished with all the synchronization. So let me produce this code. That's absolutely legal and this absolutely works. And this is what Java and the CPU does. So things outside of a synchronized block can be moved into a synchronized block, but not vice versa. You can never move code out, but you can always move code in. Good. Now we get to atomics. And that's the only way to count properly in a synchronized and shared fashion. So an atomic integer is, of course, a Java object, but at the end of the day, it's not a Java object. It's basically a machine instruction that tells the machine to do this under the hood. Have a do loop, keep a state, read the memory, try to set the memory to a new value as long as the old value is still there. If so, leave the loop. If someone else was faster, so basically what I have read before is not longer in the memory, try again. And here, once again, it is not guaranteed that this will ever finish. So there is no guarantee that this will ever finish. Worst case, your thread is basically there and tries to update and cannot because it always loses the race. In theory, this is possible. In practice, it has never been seen. So not all things in computer science are basically written in stone. Here in this case, it's possible, but unlikely. And we have to live with this unlikely likelihood, whatever. So this is all hardware supported. These are called version controlled updates. And we basically update if nothing has changed. And this is now the important part. This is a lock-free operation because we are not creating a lock. This is not a wait-free operation. So we might wait for quite some time, but we are never locking anything. So this basically means we're reading and we're writing to memory if possible, but we are probably not writing to any kind of locks. And of course, we're not preventing anyone from entering the same code. Good. Now we have basically shared mutability. And this is where you might shine with the functional programming, because functional programming is preaching immutability. If you mutate objects, it becomes really difficult to synchronize this across threads. Basically, everything that's shared is really difficult if it's mutable. So always try to design immutability into anything that's shared. If you're not sure if it's shared, make it immutable. Fix performance problems later. Design good code first. So basically, Joshua Bloch once said, classes should be immutable unless there's a very good reason to make them mutable. If a class cannot be immutable, limit its mutability as much as possible. So if you basically have a class that has one single Boolean that can be mutated, everything else is basically fix up the rest with final, make it immutable, and keep the only one thing open. So basically limit the scope of problems. So let's discuss a little bit horrible wrong code, and then we will conclude and then can do a couple of questions and answers. So on the left side, basically you see a synchronized block. I don't know if this works. You see a synchronized block against, of course, my class, the instance of my class. And we increment basically sum by some number. And then there's another one where we just read sum. This is broken, even so it might work, because the synchronized for the add basically rereads from memory and writes to memory, but the get never reads from memory. So it basically says, if I don't know this in the cache, it might come from memory. Otherwise, I might be able to put this into a register. And because a get operation here in this case is just one line of code, it might be even inlined at the end of the day. So this method might never be called. And inlining is a very efficient thing at the end of the day because it saves a lot of operations. And inlining also tries to keep things in registers as much as possible. So it might happen that this sum is then suddenly cached within your code without even knowing. Therefore, if you write something and you read it, these both have to be synchronized operations. Otherwise, it doesn't work. The second one is basically similar. Similar to the extent that, of course, our list is a reference. And this reference basically is volatile. So if I create a new list, the reference is written to memory. And if I ask for it, it's read from memory. This does not mean that the list content itself is reread completely from memory. So it might mean that you still can do operations that are not properly synchronized. If this happens in reality, depends on the implementation of the Java VM, because volatile basically synchronizes all memory. So if you basically do an add, you get all memory synchronized. That's basically currently open. But if this, for instance, is made exclusively available as an inlining operation to some other code, this code might be suddenly out of sync with reality. So volatile is really nice to keep a certain state. But of course, if this object is read from two sides or written from two sides, it's incorrect because you're only volatile basically against the reference. Even so, behind the scenes, something else might happen, but it's not guaranteed. Good. Here we have an example for the volatile, because we know that volatile basically only keeps the memory in sync and it doesn't create any block. Such an increment is totally wrong. Obviously, because it's a read, modify, write operation. So we have to take care of this by either introducing synchronized blocks, or we have to do this with an atomic integer. And the second one would be the proper operation because it's way cheaper, because it exists in hardware. It's probably just one or two additional operations instead of having a huge synchronized overhead. And this code can be inlined safely by Java, while a synchronized block can probably never be inlined safely by Java. So you always get the overhead to jumping to your method, running the synchronized code, leaving it, jumping back. So it's definitely always slower to do synchronized instead of probably selecting an atomic, for instance. But of course, sometimes it's not possible to do that. So conclusion. It's important to know what Java memory model is and what the Java memory specification states. Because as you can see here, Java leaves us a lot of room to mess around. It's also not the code that runs. So if you see code, it's definitely not the code that runs. So there are a lot of mysterious things going on at the end of the day. You have to know that. Otherwise, your code might be wrong. You know what kind of optimizations the CPU and Java can do to make your code really, really fast. And it will do this at all costs. And if you don't tell Java, hey, that's not what I want, state it. Otherwise, it will basically do everything possible. And as you might have seen in the previous minutes, it's very difficult to do code correct. And therefore, the reason is you most of the time don't want to build this yourself. You might want to rely on libraries, for instance, Akka for kind of fancy multi-threading processing of stuff. Or you might just rely on other languages if you find this a little bit too, difficult, such as Go or Rust, where you can't make these mistakes. Good. That's it. I am, strangely enough, absolutely on time. So if you have any questions, feel free to ask.
Hey, Renee, there's a question in the chat.
Yeah. Just to answer a question that hasn't been recently published, has been published about 2 or 3 years ago, but I find this one of the best Java books on earth.
That's pretty recent.
It's relatively low level. Pardon?
That's relatively recent. You're saying like 2 or 3 years ago?
Well, at least I think I bought this before the pandemic. Which basically means it's 15 years ago.
Oh, no, it says 2018.
No,
that's
yeah.
Relatively recent.
Okay.
Yeah,
It's
where
not
we
talking
see
about
the
the fancy
changes.
things.
Yeah. We
Okay.
may see some changes from some of Rene's examples as he was showing us some machine code that looked a lot more like, well, high level like the x86. It'll be interesting to see what some of that translates to when we get into the ARM, more of the RISC
Right.
scenario. You'll see many more lines. They may run faster though, but more lines of that code in order to maintain that same functionality and reliability of the language.
Could be. I know from, and Mr. Shiplev stated this in one of his Twitter rants, that it's really horrible to transfer code from Intel to ARM and vice versa. Also get the MIPS and RISC-V stuff maintained, because some of these very tricky notions about reordering fences, synchronization, that's really difficult to code and to teach the VM. And so initially some of the code was broken, so it wasn't incorrectly synchronizing. Some of the stuff was kind of, but that's the reason why we have these iterations of beta releases and stuff like that to actually find that. So it's difficult, but it has been done. And I think Microsoft also invested heavily into ARM or Java on ARM. At least I know from one of the guys I know there that the entire team, they purchased a Java company, that the entire team was basically part of this implementation.
I have a question. So regarding the final keyword. So final, if I specify an object as a final, it tells the compiler saying it's just one state, right? So as a developer, when I know that these objects values are going to change, like constant or say an array list or a hash map, I make it as a final. I add final keyword to it. Will it help the compiler to compile the code faster?
No, this is one of the mistakes I also made myself initially. So you can actually use final in a method too. You basically say never write to this variable again. That's basically protecting yourself from being a bad programmer. So I actually like this because you cannot easily reuse the same variable by accident.
Right.
But it doesn't change anything, at least not at the moment. So final doesn't cause any optimizations, and except for this fence that is put into the constructor to close things properly.
Not even the compiler saying that compile this faster, because I thought when a code is compiled, it also checks for to optimize the code or reorganize your code. So now it knows that, okay, so there's no state change for this object. So I don't have to do any additional search or optimization. No. Okay.
So for instance, if you say something like, it's private static final string foobar, that's a constant. That's optimized because the Java C compiler knows that can never change. It's static anyway. So I put this into a constant pool, and then it can be just applied all the time. So I don't even have to read this from memory. You can directly put this into the code, and we're cool. But the machine code compilation doesn't really take care of anything, especially if you use final in methods or stuff like that. There is nothing magic happening at the moment to optimize code, because the compiler already optimizes the code basically as much as it can do. So just putting things into register, bring it very close, can't get any better than that. And this doesn't matter if there's a final or not. And the rest is then basically, rely on the CPU synchronization of the caches and make sure you get always a fresh state if you want. That's basically it. So final, it's very good to protect yourself from writing bad code and accidentally overwriting things and stuff like that. So I actually like final. Final in the constructor for immutability, it's a must. If you see something that's immutable and it doesn't have final, I think this should be fixed. But beyond that, the compiler doesn't do anything special here.
Okay.
It might change in the future. Nobody says that's set in stone.
Thank you.
Thank you, René.
You're welcome. So, any more questions? I will share the slide deck later on. I think Mark will post this then, or send this around, so you can browse around. You can share this freely, whatever you want to do with it. Unless you can even give your own presentation if you like. I don't care. It's shared knowledge anyway, so I have stolen or borrowed half of it anyway, so you can do the same.
Thank you, Renee.
Cool.
All right. Thank you, Renee. I hope it cools off over there for you. I know it's heading into nighttime, right? Your time is offset. Correct.
It's currently 7 p.m. It's probably still 35 Celsius, so 95 Fahrenheit out there, at least, if not more. It probably takes another 4 to 5 hours to reach something reasonable in the upper 70s, probably. We'll see.
Well, hopefully it won't last too many more days. But thank you for thank you for presenting, and thank everyone for joining.
Anytime. And you know, if you need one more, there is one more in case you don't need another presentation.
Absolutely, we'll take you up on that. I don't know if it'll be next month or the month after, but thank you very much. I definitely, these are really good. I love the deep dive. It's been a while since I thought about some of these topics. You're muted, Garvin.
Garvin, you're muted.
Yeah, I cut my teeth on doing